You think you know where you are. Right now, as you watch this, you believe you are sitting somewhere on a small planet orbiting an ordinary star in one of the spiral arms of a galaxy called the Milky Way, and you believe that galaxy floats in an ocean of space that stretches outward endlessly in all directions. Infinity. That is the word we use to describe it. The universe goes on forever. But what if that is not true? What if the universe has an edge? Not a wall, exactly. Not a fence or a boundary you could touch. Something far stranger. Something that physics itself has been whispering about for decades. Something that, if confirmed, would rewrite everything we thought we understood about existence. What happens when you reach the end of reality? And what if the evidence we have found suggests that the end might be closer than anyone imagined? Before we descend into the abyss, let me show you the comfortable lie you have been living. For most of human history, the universe was small. The ancient Greeks believed it was a series of crystalline spheres, nested inside one another like Russian dolls, with Earth at the center and the stars fixed to the outermost shell. Aristotle called the furthest sphere the cosmos, and he believed there was nothing beyond it, not empty space, not darkness, literally nothing, no place, no time, no void. It was finite, comprehensible, bounded. Then came Copernicus, Galileo, and Newton. Earth was dethroned from the center of existence. The sun became just one star among many, and as our telescopes grew more powerful across the centuries, the universe seemed to grow with them. By the 20th century, we had discovered that the Milky Way was not the entire universe, but merely one galaxy among what we now know to be at least 2 trillion others. Each of those galaxies contains, on average, hundreds of billions of stars. The numbers became absurd, incomprehensible, beyond the capacity of the human mind to truly grasp. And somewhere along the way, scientists made an assumption. They assumed that because we could see so far, and because what we saw seemed to continue uniformly in every direction, the universe must be infinite, endless, without boundary or limit. This is not actually proven. It is an assumption, a beautiful, mathematically convenient, deeply comforting assumption. Modern cosmology is built on something called the cosmological principle. First articulated in its modern form in the early 20th century, it states that on the largest scales, the universe is homogeneous and isotropic. Homogeneous means the same everywhere. Isotropic means the same in every direction. No matter where you are in the cosmos, no matter which way you look, you would see roughly the same distribution of galaxies, the same cosmic web of matter stretching into the distance. The cosmological principle is not just philosophical convenience. It is also an observational result, at least within the limits of what we can see. The cosmic microwave background radiation, the oldest light in the universe, is uniform to 1 part in 100,000. The distribution of galaxies, when averaged over scales of hundreds of millions of light years, appears roughly even in all directions. The universe, as far as we can tell, does not have a center or a preferred direction. From the cosmological principle, combined with Einstein's general theory of relativity, flows the standard model of cosmology. In this model, space can have one of 3 possible geometries. It can be positively curved like the surface of a sphere. It can be negatively curved like a saddle. Or it can be flat like an infinite sheet of paper. The curvature depends on the total energy density of the universe compared to a critical value. If the density equals the critical density exactly, space is flat. A flat universe, in the standard mathematical description, is infinite by default. It goes on forever. If you started walking in any direction and kept walking for eternity, you would never reach an edge, never loop back around, never encounter anything but more space, more galaxies, more of the same. The European Space Agency's Planck satellite, launched in 2009, was designed to measure the cosmic microwave background radiation with unprecedented precision. The CMB is ancient light, released about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral atoms, allowing photons to travel freely through space for the first time. It is a snapshot of the infant universe, a baby picture of the cosmos taken when it was less than 1/1,000,000th of its current age. Planck's measurements of the temperature fluctuations in the CMB allowed physicists to calculate the total density of the universe. The result was extraordinary. The cosmological curvature parameter, designated by the Greek letter omega k, was found to be 0.007 plus or minus 0.0019, almost exactly zero. Within the margin of error, the universe appears to be flat. So the question is settled, right? The universe is flat, therefore infinite, therefore edgeless. You can relax, sleep well, except the Planck data contains anomalies that nobody can explain. Except there are patterns in the cosmic microwave background that should not exist if the universe is truly infinite and perfectly uniform. Except for one possibility that mainstream cosmology has largely ignored because its implications are too disturbing to contemplate. What if the universe is not flat? What if the assumption of infinity is wrong? In November 2019, a team of physicists led by Eleonora Di Valentino, along with Alessandro Melchiori and Joseph Silk, published a paper in Nature Astronomy that sent shockwaves through the cosmological community. The title was provocative: Planck Evidence for a Closed Universe and a Possible Crisis for Cosmology. The paper examined the same Planck satellite data that everyone had used to declare the universe flat. But Di Valentino and her colleagues noticed something strange, something that had been hiding in plain sight. The CMB showed an enhanced gravitational lensing effect. Light from the early universe was being bent more than the standard lambda CDM model predicted. Gravitational lensing occurs when light passes through or near massive objects. The mass curves space-time, and the light follows the curved path. The CMB photons, traveling across the universe for 13.8 billion years, encounter countless galaxies, galaxy clusters, and dark matter halos along the way. Each encounter bends the light slightly. The cumulative effect should be predictable if we know the amount and distribution of matter in the universe. But the observed lensing was stronger than expected. The Planck data showed what cosmologists call an anomalous lensing amplitude, designated as A-lens. In a universe that matches the standard model, A-lens should equal 1. Planck measured it at approximately 1.1, about 10% higher than predicted. One explanation for this anomalous lensing is that the universe is not flat at all. If space has positive curvature, if it is closed rather than flat, the geometry itself would enhance the gravitational lensing effect. The light would travel through a curved space, accumulating additional bending that mimics the effect of extra mass. Think about what that means. A closed universe is finite. It curves back on itself like the surface of a sphere, but in 3 dimensions instead of 2. If you could somehow travel in a perfectly straight line for long enough at faster than light speed to outrun the expansion of space, you would eventually return to your starting point, not because you turned around, not because you got lost, because space itself is curved into a closed shape. The Planck CMB power spectra, Valentino and her colleagues found, prefer positive curvature at more than the 99% confidence level. That is a stunning result. In statistical terms, if you assume the universe is flat, there is less than a 1% chance you would observe the data that Planck actually recorded. The universe is telling us something. Will Handley, a cosmologist at Cambridge University, published a separate analysis in August 2019, just a few months before Valentino's paper. He quantified what he called the curvature tension in the data at 2.5 to 3 standard deviations. Using Bayesian statistics, he calculated the betting odds. Without combining the CMB data with other datasets like baryon acoustic oscillations, Planck 2018 has a moderate preference for closed universes, with betting odds of over 50 to 1 against a flat universe, and over 2,000 to 1 against an open universe. Handley wrote something remarkable in his paper's conclusion. In light of the inconsistency between Planck, CMB lensing, and BAO data in the context of curved universes, cosmologists can no longer conclude that observations support a flat universe. Now, to be clear, this is not the scientific consensus. The official Planck collaboration, in their final 2018 data release, combined the CMB power spectrum data with other measurements and concluded that the universe is consistent with flatness. Many cosmologists argue that the anomalous lensing is a statistical fluke, a systematic error in the data, or an artifact of the way the likelihood analysis was performed. When you include baryon acoustic oscillations from galaxy surveys like BOSS, when you add CMB lensing data, when you combine multiple independent observations, the preference for positive curvature diminishes. But here is the thing. The different datasets are in tension with each other. If you allow curvature to vary, the Planck power spectrum data wants a closed universe, while the BAO data wants a flat one. They cannot both be right. Either there is an undetected systematic error in one of the datasets, or there is new physics we do not understand, or the universe really is closed, and we are seeing the first hints of it through the noise. Valentino and her colleagues wrote, "The assumption of a flat universe could therefore mask a cosmological crisis where disparate observed properties of the universe appear to be mutually inconsistent." A cosmological crisis. That is not language scientists use lightly. If the universe is closed, it would have a curvature radius of approximately 1 gigaparsec, or about 3.3 billion light-years. The total volume of such a universe would be finite. Calculations suggest the universe might be roughly 300 billion light-years across, vastly larger than the observable universe's diameter of 93 billion light-years, but not infinite, not endless. A very large container, but a container nonetheless. And here is where it gets strange. A closed universe does not have an edge in the conventional sense. You could not walk to the boundary and peer over it. There is no wall, no fence, no cliff at the end of space. But it does have something perhaps more unsettling. It has a fundamental limit to its extent, a shape, a size, a topology. The universe in this scenario is not the endless void we imagined. It is a bubble, a hypersphere, a three-dimensional surface curved through a fourth dimension we cannot directly perceive, finite in volume, bounded in extent, and we are inside it. But wait, there is something even more disturbing hiding in the data. Remember, the cosmic microwave background, that ancient light from the early universe. Cosmologists have studied it obsessively for decades because it contains a record of the conditions when the universe was young. The tiny temperature fluctuations in the CMB, variations of about 1 part in 100,000, are the seeds that grew into all the structure we see today. Slightly denser regions attracted more matter and eventually became galaxies. Slightly less dense regions became the voids between galaxies. The pattern of fluctuations is a fossil from the Big Bang itself. In 2004, astronomers examining data from WMAP, the Wilkinson Microwave Anisotropy Probe, discovered something they could not explain. A region of the sky, in the direction of the constellation Eridanus in the southern celestial hemisphere, was anomalously cold. Not just a little cold. The CMB Cold Spot, as it came to be known, is roughly 150 microkelvins below its surroundings. A microkelvin is 1/1,000,000th of a degree. That might not sound like much, but in a radiation field that is extraordinarily uniform across the entire sky, it is enormous. Typical temperature fluctuations in the CMB are measured in millionths of a degree, around 18 microkelvins root mean square. The cold spot, at some points, is 140 microkelvins below average. It is cold in an absolute sense, and even colder relative to the hot ring that surrounds it. And it is big. The cold spot spans about 5 degrees across the sky, roughly 10 times the apparent size of the full moon. Standard cosmological models predict that the largest temperature fluctuations should occur at angular scales of about 1 degree, corresponding to regions that were causally connected at the time of recombination. A cold spot this large, this cold, and with this particular morphology should be extraordinarily rare. The probability of such a feature arising by random chance, according to standard cosmological models, is somewhere between 1 in 50 and 1 in 200. It should not exist. One hypothesis emerged to explain the cold spot. Perhaps a supervoid, a vast region of space emptier than average, lies between us and the CMB in that direction. As CMB photons pass through a void, they experience something called the integrated Sachs-Wolf effect. The photons fall into the void's gravitational potential well, gaining energy, then climb back out, losing energy. If the universe were not expanding, these effects would cancel out. But because the universe is expanding, and because dark energy is accelerating that expansion, the photon loses slightly more energy climbing out than it gained falling in. The net result is a redshift, a loss of energy, which makes the CMB appear colder in that direction. In December 2021, the Dark Energy Survey confirmed that a supervoid does indeed exist in the direction of the cold spot. The Eridanus supervoid, as it has been named, is one of the largest structures ever mapped by humanity. It lies somewhere between 6 and 10 billion light-years away and spans roughly 500 million to 1 billion light-years across. It is almost entirely empty of galaxies, a cosmic ghost town in a universe otherwise teeming with structure. The Dark Energy Survey team, led by Andras Kovacs, used data from the 570 megapixel dark energy camera mounted on the Blanco telescope in Chile to map the distribution of dark matter in that region of the sky. They found that the supervoid is real, that it is aligned with the cold spot, and that it would produce a temperature decrement via the integrated Sachs-Wolf effect. But here is the problem. The supervoid can only explain a fraction of the cold spot's anomaly. Different analyses estimate the contribution at somewhere between 10 and 50%. Even the most generous calculations leave the majority of the temperature deficit unexplained. A June 23 multi-probe study integrating CMB maps, galaxy clustering statistics, and weak lensing convergence fields tested the supervoid hypothesis rigorously. The researchers looked for the lensing signal that would be expected if a large void were responsible for the cold spot. They found that the observed lensing signal does not match predictions for a void large enough to explain the anomaly. In their analysis, the supervoid hypothesis was effectively ruled out. Something else is responsible. And one of the proposed explanations is so radical that many cosmologists refuse to take it seriously. Laura Mersini-Houghton is a theoretical physicist and cosmologist at the University of North Carolina at Chapel Hill. Born in Albania, she came to the United States as a Fulbright scholar and has spent her career working on some of the deepest problems in physics: the origin of the universe, the nature of dark energy, and the landscape of string theory. In a series of papers beginning in 2004, Mersini-Houghton developed a theory that our universe is not alone. Drawing on string theory and the concept of eternal inflation, she proposed that the Big Bang was not the beginning of everything, but rather the moment when our particular bubble universe nucleated from a vast, eternally inflating spacetime. In eternal inflation, quantum fluctuations cause regions of space to tunnel into different vacuum states, each one potentially giving rise to a separate universe with its own physical constants. These bubble universes expand independently, possibly forever. The multiverse, if it exists, would contain an unimaginably vast or even infinite number of such bubbles, most of them inaccessible to each other. But Mersini-Houghton realized something crucial. Before cosmic inflation separated these bubbles, when they were still quantum mechanically connected, they would have been entangled. Quantum entanglement creates correlations between particles that persist even when they are separated by vast distances. And the entanglement between our universe and its neighbors, she argued, might have left observable signatures in the cosmic microwave background. In 2006 and 2007, Mersini-Houghton and her collaborators made a series of testable predictions. They predicted that entanglement with the landscape multiverse would suppress the amplitude of large-scale fluctuations in the CMB, creating a lack of power at low multipoles. They predicted a hemispherical asymmetry in the CMB temperature. They predicted a preferred direction in the universe, a flow of structure toward a particular point in the sky. And they predicted the existence of a giant void in the southern hemisphere, roughly 12 degrees across, where the gravitational pull of our neighboring universe would create an underdensity. The cold spot was confirmed by WMAP data released in 2004 and 2005, just as Mersini-Houghton was developing her theory. She claimed, controversially, that the cold spot is the unmistakable imprint of another universe beyond the edge of our own. It is not a void. It is not a statistical fluke. It is the place where our universe is bumping against a neighboring bubble, where the quantum entanglement between them has left a scar in the oldest light we can see. In 2007, she told New Scientist magazine, It is the unmistakable imprint of another universe beyond the edge of our own. This claim is controversial, to put it mildly. Many physicists reject the multiverse as untestable metaphysics. The specific mechanism Mersini-Houghton proposes, involving quantum entanglement across the landscape of string theory vacua, has been disputed. A 2016 analysis by Will Kinney using Planck data combined with bicep Char-Keck polarization measurements found no evidence for observable modulations to the power spectrum from landscape entanglement, and no sourcing of observable CMB anomalies. Yet the anomalies persist. The cold spot exists. The power deficit at low multipoles exists. The hemispherical asymmetry exists. Conventional explanations have failed to fully account for them, and Mersini-Houghton's predictions, whatever their theoretical basis, were made before the detailed observations confirmed the phenomena. In 2022, she published a book titled Before the Big Bang: The Origin of Our Universe from the Multiverse, laying out her case for the general public. If she is right, the cold spot is not just an anomaly. It is evidence of an edge, the place where our universe ends and something else begins. A boundary not in the sense of a wall, but in the sense of a contact surface between two fundamentally separate domains of existence. Our universe, in this picture, is a bubble floating in an infinite foam of other bubbles, and the cold spot marks where we are pressed against our neighbor. The idea of a cosmic edge is not new, it is ancient. Archytas of Tarentum, a Pythagorean philosopher of the 5th century BCE, posed a famous paradox that philosophers have struggled with for 2.5 millennia. If I stand at the supposed boundary of the cosmos, can I stretch out my hand beyond it? If yes, then the boundary is not truly the edge, and there must be space beyond it. If no, then what stops my hand? A wall. What is the wall made of? What is on the other side of the wall? For millennia, this paradox seemed to demand an infinite universe. Any edge implied something beyond the edge. The concept of a true boundary seemed incoherent, self-contradictory, philosophically absurd. But modern physics offers a way out, a resolution that Archytas could never have imagined. A universe can be finite and yet have no edge. Consider the surface of the Earth. It is finite. You could measure its total area, approximately 510 million square kilometers. You could count every atom on its surface if you had the patience and the tools. It is bounded in extent, but it has no edge. There is no cliff where you might fall off the planet. If you walk in a straight line on Earth's surface, what happens? You do not hit a wall. You do not reach a boundary. You simply return to where you started. The surface curves back on itself. It is finite and unbounded. Now extend this concept to 3 dimensions. Imagine a space that curves back on itself, like the surface of a sphere, but in one higher dimension. This is hard to visualize because our brains evolved to navigate 3-dimensional Euclidean space, not 4-dimensional curved manifolds. But mathematically, it is perfectly coherent. A closed universe with positive curvature is like a 3-dimensional hypersphere. The 3 dimensions of space that we experience are analogous to the 2 dimensions of Earth's surface. We can move in any direction we like. We never encounter a wall, but the total volume of space is finite, and if we could somehow travel fast enough, we would eventually return to our starting point. The edge is not a location. It is a property of the geometry itself. The universe does not stop somewhere. It curves. This sounds almost comforting. No wall, no barrier, no physical boundary to contemplate. You cannot reach the edge of the universe because there is no place where the edge is located. But think about what it implies. In an infinite universe, every possible arrangement of matter occurs somewhere. Given enough space, given infinite volume, every configuration of atoms that is physically possible must happen, not just once, but infinitely many times. There would be another Earth somewhere, another you, another version of this exact moment playing out. Not in some parallel dimension, but simply far, far away in the same universe, beyond our observable horizon. Infinity makes everything repeatable, everything recoverable. Nothing is truly lost, because every pattern that exists will recur endlessly. In a finite universe, there is only so much room. Only so many configurations of matter can fit. Only so many possibilities can be realized. The same patterns might never repeat. You might be genuinely unique in the entire cosmos, not because you are special in any meaningful sense, but simply because the universe does not have enough volume for there to be another arrangement of atoms exactly like the one that makes you. You are not one of infinitely many. You are one of a finite number, perhaps a very large finite number, inconceivably large, but finite nonetheless. And finite things can end. Even if we set aside the question of the universe's overall shape, whether it is flat or curved, infinite or finite, there is another kind of edge that physics has proven beyond any doubt. An edge we can calculate with precision. The observable universe has a boundary. Light travels at a fixed speed, approximately 299,792 kilometers per second in vacuum. Nothing in the universe can carry information faster than this. The universe is approximately 13.8 billion years old, according to our best current measurements. You might think, therefore, that we can see objects up to 13.8 billion light-years away, objects whose light has been traveling toward us since the beginning of time. But you would be wrong. The universe has been expanding since the Big Bang. Space itself has been stretching, carrying galaxies apart like raisins in rising bread dough. Objects that emitted light 13.8 billion years ago are now much farther away than they were then. The light has been traveling through an expanding medium, and during its journey, the source has receded. The current radius of the observable universe, what cosmologists call the particle horizon, is about 46.5 billion light-years. This is not the distance light has traveled, but the present-day distance to the most distant objects whose light can reach us. Beyond that radius, there are regions of space from which light has not had time to reach Earth since the Big Bang. We cannot see them. We cannot receive any signal from them. We cannot know anything about them through direct observation. They exist, presumably. The standard model assumes that space continues beyond our horizon, filled with more galaxies, more stars, more of the same. But we have no empirical access to that realm. For all practical purposes, it is outside our reality. This is the particle horizon, the boundary of the observable universe, the edge of what we can see. But there is an even more disturbing boundary, the cosmic event horizon. The expansion of the universe is not constant. It is accelerating. In 1998, two independent teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, made a discovery that revolutionized cosmology. By measuring the distances and redshifts of distant Type I supernovae, they found that the expansion of the universe is speeding up, not slowing down as everyone had expected. This acceleration is attributed to a mysterious phenomenon called dark energy. We do not know what dark energy is. We know only what it does. It causes space to expand at an accelerating rate. Dark energy comprises approximately 68% of the total energy content of the universe, making it the dominant component by far. Ordinary matter, the stuff we are made of, accounts for less than 5%. Dark matter, equally mysterious but better understood, makes up about 27%. Dark energy is the majority shareholder in the cosmos. Because of accelerating expansion, galaxies beyond a certain distance are receding from us faster than light, not moving through space faster than light, which would violate Einstein's special relativity. Rather, the space between us and them is expanding so quickly that light emitted from those regions today will never reach us, no matter how long we wait. The expansion outruns the light. The current distance to our cosmic event horizon is about 16 billion light-years, or roughly 5 gigaparsecs. This is the co-moving distance to regions of space that are just barely reachable. If we sent a light signal right now, it could just barely reach galaxies at this distance before the expansion carried them forever beyond our reach. Anything farther than this is already unreachable, already outside our future light cone, already gone, and it is getting worse. As Ethan Siegel, the astrophysicist and science communicator, explains, dark energy makes distant galaxies recede from us ever faster in our expanding universe. In models where dark energy behaves like a cosmological constant, and current observations suggest it does, the universe will expand exponentially over time, approaching what physicists call a de Sitter state. What does this mean for the future? As time passes, galaxies that are not gravitationally bound to us will accelerate away beyond our cosmic event horizon. The light from them will become progressively more redshifted, stretched by expansion to longer and longer wavelengths. At first, they will merely grow dimmer and redder. Eventually, they will fade from the visible spectrum entirely into infrared, then microwave, then radio, and then they will vanish completely. Their light so stretched that it becomes undetectable, their presence so redshifted that nothing remains to observe. One by one, the galaxies will disappear from our sky. The cosmic microwave background itself, the oldest light in the universe, will eventually suffer the same fate. Over vast timescales, the CMB will be redshifted to longer and longer wavelengths. Its temperature will drop toward absolute zero. Eventually, its frequency will become so low that it will be absorbed by the interstellar medium within our own galaxy, screened from any observer inside the Milky Way. In the far future, perhaps 100 billion years from now, or perhaps 1 trillion years, any civilization existing in our region of space would see only its local group of galaxies, bound together by gravity and slowly merging into a single giant elliptical galaxy. The rest of the universe would be dark, silent, unreachable, all evidence of the Big Bang, all evidence that other galaxies ever existed, all evidence of the cosmic structure that we can see today, would be gone. A civilization arising in that far future, if one did arise, would look up at a nearly empty sky and conclude that they lived in an island universe, a single galaxy floating alone in an infinite void. They would have no way of knowing that trillions of other galaxies once existed, that the universe was once filled with light and matter and structure extending in all directions. The evidence would be erased. not by any catastrophe, but by the simple passage of time and the relentless expansion of space. The edge is not just spatial, it is temporal. The walls are closing in, and now we arrive at the most unsettling possibility of all. What if the edge of the universe is not a feature of physical space, but of information itself? What if reality has a resolution limit, a fundamental boundary beyond which nothing can be distinguished? Not because our instruments are too crude, but because distinction itself becomes meaningless. In 1993, the Dutch theoretical physicist Gerard Hooft proposed an idea that would transform our understanding of space, time, and reality. Building on insights from black hole physics, he suggested that the information content of any region of space is not proportional to its volume, as you might intuitively expect, but to its surface area. This is profoundly counterintuitive. If you have a room full of furniture, you would think the amount of stuff in the room depends on how big the room is, not on how big its walls are. More volume means more room for things. But 't Hooft argued that gravity changes everything. In a gravitational system, the maximum information content is bounded by the area of the boundary. Leonard Susskind, one of the founders of string theory, developed this idea further in 1995, giving it a name, the holographic principle. Susskind combined Hooft's insight with his own work on black holes and string theory to propose something startling. The holographic principle states that all the information contained within any volume of space can be encoded on the boundary of that space. Like a hologram, where a two-dimensional surface contains all the data needed to reconstruct a three-dimensional image, the entire contents of a region of space might be describable by information stored on a distant, lower-dimensional surface. Susskind put it this way: the three-dimensional world of ordinary experience, the universe filled with galaxies, stars, planets, houses, boulders, and people, is a hologram, an image of reality coded on a distant two-dimensional surface. This is not mysticism. It is not metaphor. It emerges directly from the mathematics of black holes. In the 1970s, Jacob Bekenstein realized something remarkable about black holes. A black hole has entropy, a measure of its information content, or equivalently, its microscopic complexity. Bekenstein showed that the entropy of a black hole is proportional to the area of its event horizon, not to its volume. Later, Stephen Hawking refined the calculation and derived what is now called the Bekenstein-Hawking entropy formula. The event horizon of a black hole, that boundary from which nothing can escape, contains all the information about everything that ever fell inside. The information is not lost, as Hawking initially feared. It is encoded on the horizon itself, 1 bit of information per Planck area. A Planck area is unimaginably small, about 10 to the negative 70 square meters, but it sets a fundamental limit. If the holographic principle is correct, and there is substantial theoretical evidence that it is at least approximately correct, then our three-dimensional reality is in some sense a projection. The true description of physics exists on a boundary surface, and the interior that we experience is derived from it. For black holes, the boundary is the event horizon. For the universe as a whole, the boundary is something more subtle. Different formulations of cosmological holography propose different surfaces: the cosmic event horizon, the particle horizon, or an abstract boundary at spatial infinity. But regardless of the details, the implication is profound. The universe has a finite information capacity. There is a maximum number of bits that can be stored in any given region of space, and that number is determined not by volume, but by surface area. Jacob Bekenstein estimated that the visible universe contains at least 10 to the 100th power bits of entropy. That is a 1 followed by 100 zeros, an inconceivably large number. But it is not infinite. The holographic bound tells us that no matter how large the universe is, there is a limit to how much it can contain, a limit to complexity, a limit to the number of possible thoughts, possible structures, possible histories. If the universe is a hologram projected from its boundary, then the edge is not somewhere you could travel to. You cannot walk to the boundary because you are already part of the projection. The edge is the surface from which reality is rendered. It is not a wall in the distance. It is the screen on which you are drawn. There is a pattern hiding in the cosmic microwave background that should not be there. When WMAP and later the Planck satellite mapped the CMB in exquisite detail, scientists expected to find temperature fluctuations distributed randomly across the sky with no preferred direction, no special orientation. The cosmological principle demands this. If the universe is the same everywhere and in every direction, then its oldest light should reflect that uniformity. Instead, they found alignments. The CMB can be decomposed mathematically into spherical harmonics, a series of patterns at different angular scales. The monopole is the average temperature across the whole sky. The dipole has 2 lobes, a hot side and a cold side, and is dominated by our motion through the universe, which Doppler shifts the CMB. Beyond the dipole are the quadrupole with 4 lobes, the octupole with 8 lobes, and so on to higher and higher multipoles. In a random, isotropic universe, these multipoles should point in random directions, uncorrelated with each other and uncorrelated with anything in our solar system. But the quadrupole and octupole of the CMB are aligned with each other. Their symmetry axes point in nearly the same direction within a few degrees. This is statistically improbable. And even more disturbing, both of them appear to align with the plane of the solar system and with the direction of Earth's motion relative to the CMB. Kate Land and João Magejo, 2 cosmologists, analyzed this alignment in a 2005 paper. They dubbed it the axis of evil because its implications were so troubling for standard cosmology, an ironic reference to George W. Bush's rhetoric about rogue nations that was politically salient at the time. Why would the oldest light in the universe care about our solar system? The CMB was released 380,000 years after the Big Bang, more than 13 billion years ago. Our sun did not form until about 4.6 billion years ago. The solar system did not exist when the CMB was created. There should be absolutely no connection between the geometry of our local planetary system and the large-scale patterns in ancient cosmic radiation. Data from the Planck telescope, published in 2013 and refined in 2018, confirmed the anomaly. The alignment persisted. In March 2024, a study published in Astronomy and Astrophysics analyzed the latest Planck data using a directional analysis of temperature-temperature angular correlations. The researchers found a preferred axis in the CMB, pointing in the direction of galactic coordinates roughly 260 degrees longitude and minus 50 degrees latitude at the 98 to 99% confidence level. The paper concluded, this highly significant dipole term observed in the sigma map reveals the hemispherical asymmetry in the angular correlations of the CMB sky. Dominique Schwartz of the University of Bielefeld, one of the researchers who has studied these anomalies for years, said in 2013, "For a long time, part of the community was hoping that this would go away, but it hasn't. The anomaly is robust. It appears in different datasets from different experiments. It persists through different analysis methods. It is not an artifact of foreground contamination or instrumental systematics as far as anyone can tell." What does it mean? One possibility is that it is a statistical fluke, a random alignment that happens to look meaningful but has no deeper cause. With enough data, some unusual patterns will appear by chance. Perhaps we are seeing faces in clouds. Another possibility is that there is some unknown systematic error or foreground contamination that has not been properly subtracted. The CMB data must be cleaned of galactic emission, of detector noise, of various instrumental effects. Perhaps the alignment is an artifact of this cleaning process. But a third possibility is more unsettling. Perhaps the universe really does have a preferred direction. Perhaps isotropy, the assumption that the cosmos looks the same in all directions, is wrong. If the universe has a preferred direction, it has structure on the larger scales. It has an orientation. It has, in some sense, an axis. Structure implies boundaries. An oriented universe is a shaped universe, a cosmos with features that distinguish one direction from another. And a shaped universe might have edges, places where the shape ends or curves back, or changes character. Or consider an even stranger possibility. The axis of evil might point towards something, perhaps not the center of a finite universe, which in a positively curved space has no meaning, but perhaps toward a feature of the cosmic topology, a symmetry axis of a multiply connected space, or toward the direction of our nearest neighbor in a bubble multiverse. We do not know. That is the honest answer. The anomalies persist, and we do not know what they mean. Let us step back and assemble what we have found. The Planck data, examined closely, shows evidence for positive curvature at the 99% confidence level. If this is not a statistical fluke or systematic error, the universe is closed and finite, perhaps 300 billion light-years across, curving back on itself like a vast hypersphere. The CMB Cold Spot, 7 times colder than typical fluctuations and far larger than standard physics predicts, cannot be fully explained by a supervoid along the line of sight. One hypothesis is that it marks the impact site of another universe, a bruise from where our bubble touched a neighboring bubble in the multiverse. The axis of evil shows alignments in the CMB that should not exist if the universe is truly uniform and infinite. Something is breaking the symmetry. Something is imposing structure on the cosmos at the larger scales. Dark energy is accelerating the expansion of the universe, pushing everything beyond our cosmic event horizon, creating an edge beyond which we can never see, never reach, never know. The holographic principle suggests that all information about the universe is encoded on a boundary surface, that the 3 dimensions we experience are a projection from a 2-dimensional edge, and the observable universe itself has hard limits, a particle horizon at 46.5 billion light-years and an event horizon at 16 billion light-years, boundaries set by the speed of light and the age and expansion history of the cosmos. We are surrounded by edges, hemmed in on every side. The infinite universe was always a comforting assumption, never a proven fact. Some cosmologists and philosophers have tried to make sense of these edges by proposing that our universe is a simulation. In 2003, the philosopher Nick Bostrom at Oxford University published a paper titled "Are You Living in a Computer Simulation?" that laid out what he called the simulation argument. Bostrom reasoned as follows: if future civilizations develop enormous computing power, and if they have any interest in simulating their ancestors or creating artificial worlds, then the number of simulated beings would vastly outnumber real beings. If simulations are possible and desirable, they would proliferate. And if you are a conscious being without specific information about whether you are simulated or real, you should assign a probability to each possibility based on the numbers. Given enough simulations, most conscious beings who ever exist would be simulated. We might be among them. Under the simulation hypothesis, the edge of the universe is simply the boundary of our simulation, the limits of the computing power available to our simulators, the resolution at which our reality is rendered. This might explain certain features of physics. The Planck length, the smallest meaningful unit of distance, at about 10 to the negative 35 meters, might be the pixel size of our simulated universe. The speed of light might be a processing constraint, a limit on how fast information can be updated in the simulation. The cosmic event horizon might be the boundary beyond which the simulators do not bother to render, because no one inside the simulation will ever observe it. The CMB anomalies, the alignments, the cold spot might be artifacts, compression glitches, or Easter eggs left by bored programmers. This is a fun idea to contemplate, and some serious physicists have engaged with it. But it does not save us from the edge. It merely relocates it. The walls are still there. They are made of code rather than space-time, imposed by simulators rather than physics, but they constrain us just as effectively. And there is something even more disturbing about the simulation hypothesis. Simulations can be paused. Simulations can be stopped. The edge of a simulated universe is not just spatial, it is existential. If we are simulated, our continued existence depends on the choices of beings we can neither perceive nor influence. But here is the thing about edges. They are also beginnings. Consider the history of cosmology. Every time we have encountered a limit to the cosmos, we have found ways to see beyond it, or at least to reconceive it. In 1917, Albert Einstein proposed the first modern cosmological model based on his general theory of relativity. He assumed the universe was static, eternal, unchanging. Stars had always existed and would always exist. The cosmos was a fixed stage on which the drama of physics played out. To make the mathematics work, to prevent gravity from causing the universe to collapse, Einstein introduced a fudge factor into his field equations. He called it the cosmological constant, represented by the Greek letter lambda. This constant provided a kind of cosmic repulsion that balanced gravity, keeping the universe stable. Arthur Eddington, the British astrophysicist, showed in 1930 that Einstein's model was unstable. Any tiny perturbation would cause the universe to expand or contract. The static universe was balanced on a knife's edge, and the slightest nudge would send it tumbling into motion. When Edwin Hubble discovered in 1929 that galaxies are receding from us, that the universe is expanding, Einstein abandoned the cosmological constant. He reportedly called it his greatest blunder. But in 1998, when astronomers discovered that the expansion is accelerating, they needed something to explain the acceleration. Dark energy, which behaves exactly like a cosmological constant. Einstein was wrong, then right, then wrong again, then vindicated decades after his death. The edge of our understanding keeps shifting. The boundaries we accept today may be transcended tomorrow. What if the edges we have identified, the cosmic event horizon, the closed curvature, the holographic boundary, are not final limits, but invitations, challenges to our ingenuity, frontiers to be explored? The first fish that crawled onto land faced an edge. The ocean ended and something unknown began. The first humans who sailed beyond the horizon faced an edge. The familiar world ended and uncertainty began. The first astronauts who left Earth's atmosphere faced an edge. Gravity's embrace ended and the void began. Each time, the edge was real. Each time, it was crossed. We are explorers. It is what our species does. We push against limits. We map the unknown. We ask what lies beyond. So what happens when you reach the end of reality? Perhaps you find that the end is not a wall. It is a mirror. The edge reflects back everything we are, everything we might become. It shows us the shape of our condition, the limits of our reach, the boundaries of what we can know. And it asks us a question, not what lies beyond. We may never answer that. But what will we do with what is here, inside the edge, in the finite time and finite space we have been given? The universe has an edge, and so do we. Our lives are bounded by birth and death. Our knowledge is bounded by the reach of our instruments and the capacity of our minds. Our civilizations are bounded by the resources of our planet and the span of our social cohesion. But within those bounds, we have accomplished astonishing things. We have built cathedrals that took generations to complete. We have written symphonies that bring audiences to tears centuries after the composer's death. We have discovered the mathematics of space-time and the poetry of the quantum world. We have sent robots to Mars and telescopes to peer at the edge of the observable universe. If the universe is a container, then we are its contents, and the contents can matter. The edge is not the end of the story. It is the shape of the canvas. What we paint on it is up to us. The Planck satellite measured the cosmic microwave background to a precision of 1 part in a million. It found anomalies that challenge our assumptions about infinity and uniformity. The Dark Energy Survey mapped the largest supervoid ever detected, but that void cannot fully explain the cold spot. Laura Mersini-Houghton predicted features of the CMB from her multiverse theory, and those predictions, remarkably, match the data. The holographic principle tells us that information is bounded, that reality might be encoded on a distant surface, that the universe has a finite capacity for complexity. Dark energy is accelerating the expansion, shrinking our accessible cosmos over time, creating an event horizon that will eventually swallow all evidence of the wider universe. And we, on our small planet, orbiting an ordinary star in an unremarkable galaxy, are the ones asking these questions. We are the matter of the universe contemplating its own boundaries. We are the cosmos made conscious, looking at itself and wondering what it is, where it ends, what might lie beyond. That is not nothing. That is extraordinary. The universe may have an edge. That edge may be closer than we thought, and its nature may be stranger than we imagined. But we are here, at this moment, peering into the darkness and asking what we might find. That is what makes us who we are. And if the universe has an edge, then we are the witnesses to it, the only ones, perhaps, in this vast, finite cosmos who know it is there. Maybe we will find a way beyond. Maybe we will not. But the looking, the wondering, the asking, that is the most human thing there is. And in a universe that may be bounded, in a cosmos that may be finite, in a reality that may have edges on every side, we persist, we question, we explore. Because that is what conscious beings do when they find themselves inside a container. They look for the lid. There is one more thing I want to tell you about edges. In topology, the branch of mathematics that studies the properties of shapes that remain unchanged under continuous deformation, there is a concept called a manifold. A manifold is a space that looks locally like ordinary Euclidean space, but may have a very different global structure. The surface of a sphere is a two-dimensional manifold. At any point on the surface, if you look at a small enough region, it appears flat. You could lay a small sheet of paper on the ground, and it would seem to fit perfectly. But the global structure is curved. Walk far enough in any direction, and you return to where you started. The universe, according to general relativity, is a four-dimensional manifold, 3 dimensions of space, plus 1 of time, all curved by the presence of matter and energy. The local geometry, the curvature you would measure in any small region, is determined by the distribution of mass nearby. But the global topology, the overall shape and connectedness of the cosmos, is not specified by Einstein's equations. It must be determined observationally or assumed. For decades, cosmologists assumed the simplest topology, simply connected space, the 3-dimensional analog of either a flat plane, a sphere, or a saddle, depending on curvature. But there are far more exotic possibilities. The universe could be multiply connected. It could be shaped like a 3-dimensional torus, where if you travel far enough in one direction, you emerge from the opposite side, like a character in a video game crossing from the right edge of the screen to appear on the left. Or it could be a Poincaré dodecahedral space, a positively curved manifold with a topology of a dodecahedron, 12 pentagonal faces glued together in a particular pattern. In 2003, Jean-Pierre Luminet and his colleagues at the Paris Observatory proposed that the universe might be a Poincaré dodecahedral space. They claimed that this topology could explain certain anomalies in the CMB power spectrum, particularly the lack of power at the largest angular scales. The idea generated excitement and controversy. If the universe has a complex topology, if it is multiply connected on scales comparable to the observable universe, then we might be able to detect it. We would see the same cosmic structures appearing in different directions in the sky, like looking into a hall of mirrors. Astronomers have searched for these matched circles in the CMB, regions where the temperature patterns on opposite sides of the sky correlate in the way predicted by multiply connected topologies. So far, the searches have come up empty. The universe appears to be simply connected on scales at least as large as the observable universe. If it has a complex topology, if space wraps back on itself, it does so on scales far beyond what we can see. But absence of evidence is not evidence of absence. The universe might be multiply connected on scales only slightly larger than our horizon. We might be just barely unable to see the signature, or the topology might be more subtle, requiring different search methods than those employed so far. The point is that the shape of the universe, its topology as well as its geometry, remains an open question. The edge, if there is one, might not be a simple surface. It might be a complex, multiply-connected structure that folds back on itself in ways we have not imagined. The universe is stranger than we know, perhaps stranger than we can know. Consider the future of cosmological research. The James Webb Space Telescope, launched in December 2021, is now producing images of unprecedented depth and clarity. It is revealing galaxies from the first few 100 million years after the Big Bang, offering a glimpse into the cosmic dark ages that followed the release of the CMB. These observations are refining our understanding of structure formation, the growth of galaxies, the evolution of the cosmos. The Vera C. Rubin Observatory in Chile, with the largest digital camera ever built, is preparing to conduct the legacy survey of space and time. Over 10 years, it will map billions of galaxies, track millions of supernovae, and measure the expansion history of the universe with unprecedented precision. The data it gathers will constrain dark energy models and test whether the accelerating expansion is truly driven by a cosmological constant or by something more exotic. The DESI experiment, the Dark Energy Spectroscopic Instrument, is already gathering spectra of millions of galaxies and quasars, mapping the baryon acoustic oscillations that serve as a standard ruler for measuring cosmic distances. Early results from DESI, released in 2024, have hinted at possible deviations from the standard lambda CDM model, suggesting that dark energy might evolve over time rather than remaining constant. If confirmed, this would revolutionize our understanding of the cosmos. The European Space Agency's Euclid mission, launched in 2023, is creating a three-dimensional map of the universe spanning billions of light years. By measuring the weak gravitational lensing of distant galaxies and the clustering of matter on large scales, Euclid will probe both dark energy and dark matter, testing whether general relativity holds at cosmological distances. Each of these experiments might discover something that changes everything: a deviation from flatness, evidence for cosmic topology, signs of a boundary or a bubble collision, or confirmation that our current models are correct and the universe is indeed flat and infinite and uniform on the largest scales. We stand at a moment of potential transformation. The questions we have been asking for a century about the size and shape and fate of the cosmos might be answered within our lifetimes. Or we might discover that the answers are more complex and more strange than we ever anticipated. There is a philosophical dimension to the question of cosmic edges that science alone cannot resolve. If the universe is finite, what does that mean for the significance of existence? In an infinite cosmos, everything possible happens somewhere. Every book that could be written has been written. Every life that could be lived is being lived. There is nothing unique, nothing unrepeatable, nothing truly lost. In a finite cosmos, uniqueness returns, scarcity returns. The particular matters because there is no guarantee of repetition. Your thoughts might be the only instance of those thoughts in all of existence. Your choices might be genuinely singular, not echoed endlessly in an infinity of parallel realms. Some find this terrifying. The vastness of infinity offers a kind of comfort, a guarantee that nothing truly ends because everything repeats. The finitude of a bounded cosmos offers no such reassurance. Others find finitude liberating. If existence is bounded, then what happens here, in this bounded realm, has weight and significance that an infinite cosmos cannot provide. The edge makes everything precious. Both responses are valid. Both are human. The universe does not care which perspective we adopt. It simply is what it is. And we are the ones who must make meaning from it. Let me tell you about the last photons. As the universe expands and galaxies recede beyond the event horizon, as the cosmic microwave background fades to undetectability, as dark energy drives all distant matter beyond the reach of any signal, what remains? The local group of galaxies, the Milky Way and Andromeda, and a few dozen smaller companions will eventually merge into a single giant elliptical galaxy. Astronomers sometimes call this future galaxy Milkdromeda. It will contain hundreds of billions of stars, remnants of both parent galaxies, swirling in new orbits around a common center. Stars will continue to form for billions of years, until the gas supply is exhausted. Then the stellar fires will dim one by one. Red dwarfs, the smallest and longest-lived stars, will burn for trillions of years, far longer than the current age of the universe. But even they will eventually exhaust their hydrogen and cool to darkness. Brown dwarfs, failed stars too small to sustain nuclear fusion, will radiate their heat into space over even longer timescales. White dwarfs, the cooling corpses of sun-like stars, will slowly crystallize and fade. Neutron stars will spin down and cool. Black holes will swallow whatever falls into them and slowly evaporate via Hawking radiation over timescales that dwarf the current age of the cosmos by factors of 10 to the 60th power or more. In the very far future, all that remains are black holes and cold dead stars and drifting particles spread across a cosmos grown to unimaginable size. The temperature will approach absolute zero. The last meaningful processes will cease. This is the heat death of the universe, the final equilibrium from which no further complexity can emerge. At some point, the last photon emitted by the last star will have redshifted beyond any possibility of interaction. The last bit of cosmic microwave background radiation will have diluted to nothing. The universe will be dark, cold, empty, eternal. This is the ultimate edge, the boundary not in space but in time, the end of all things that happen, all structures that form, all stories that unfold. But here is the strange thing. Even at that final edge, something persists. The laws of physics remain. The geometry of space-time endures. The information encoded in the arrangement of particles, though inaccessible and irretrievable, is not destroyed. According to some interpretations of quantum mechanics, information can never be truly lost. The universe, even in its final state, retains a kind of structure. It is not nothing. It is a very particular something, the outcome of everything that came before it, the final state of all the matter and energy and space-time that once flared with stars and galaxies and life. The edge of time is not the absence of existence. It is the completion of it. I began by asking what happens when you reach the end of reality. Now I think the answer is clear. You do not reach the end. The end reaches you. The edges of the universe, whether in space or time or information, are not walls you encounter. They are limits that shape what is possible. They are not obstacles, but conditions. They are not barriers, but the structure of existence itself. We live inside these edges. We always have. We always will, for as long as we exist at all. The particle horizon sets the boundary of what we can see. The event horizon sets the boundary of what we can reach. The holographic bound sets the boundary of what can exist. The curvature of space, if the universe is closed, sets the boundary of how far space extends. And the heat death, if current physics is correct, sets the boundary of how long meaningful structure can persist. We are bounded creatures in a bounded cosmos. That is not a tragedy. It is the condition of being real. Infinite things are abstractions. Finite things are actual. We are actual, and so is the universe we inhabit. The edges define us. They give shape to our existence. They make possible the very concept of location, of duration, of selfhood. Without edges, without limits, without boundaries, there is no here as opposed to there, no now as opposed to then, no self as opposed to other. The edge is not the enemy of existence, it is its prerequisite, and so we return to where we began. You think you know where you are, and now perhaps you know a little more. You are inside a cosmos that may be finite, bounded by curvature that closes space back on itself. You are surrounded by horizons that limit what you can see and reach. You are encoded, perhaps, on a distant surface from which your three-dimensional experience is projected. You are made of matter that will eventually scatter into the cold dark of heat death. You are, in every sense, at the edge, but you are also the universe become conscious. You are matter arranged in patterns complex enough to contemplate its own condition. You are the cosmos looking at itself and asking what it is. That is not nothing. In a finite universe, in a bounded existence, in a reality hemmed in by edges on every side, something extraordinary has happened. The universe has produced beings who can understand edges, who can map horizons, who can theorize about boundaries, who can ask with wonder and terror what lies beyond. Maybe we will find the answer, maybe we will not, but we are asking, and that matters. The edge is out there. The edge may also be right here, encoded in the fabric of space and time and information that constitutes everything we are. And we are the witnesses, the only witnesses, perhaps, that this particular arrangement of matter and energy will ever produce. Look up at the stars tonight, if you can. Remember that the light you see left those stars years or centuries or millennia ago. Remember that beyond what you can see lies more, always more, until somewhere out there the cosmic event horizon draws a line that can never be crossed. Remember that the universe had a beginning and may have an end, that it may have a shape and a size, that it may be finite in ways we are only beginning to understand. And remember that you are part of it, not separate from it, not observing it from outside. You are inside the edge, made of the same stuff as stars and galaxies and cosmic microwave radiation. The universe is looking at itself through your eyes, and it is wondering what it is. That is the final thought I want to leave you with. Not fear of the edge, not despair at the boundaries. Wonder. The universe has edges, and somehow, against all odds, it has produced beings who can stand at those edges and ask what lies beyond. That is the most remarkable thing that has ever happened, and you are part of it.